Hi, good afternoon to you all. I welcome you to the monthly Android webinar series. And to kick off this whole series, today I will be talking about Introduction to NDK Programming and Android for Intel Architecture. Since there is some delay in the broadcast, like there is almost a minute delay, so please enter all your questions in the comments tab below, and I will be taking up the questions at the end of this session. To begin with, I will be talking about the following points. Why build Android apps for Intel architecture? What is NDK and why is the NDK needed? How to use the NDK, that is how to develop the NDK applications. How to handle the Java objects and the JVM objects from the native code. Then I will be talking about optimizing your NDK application for Intel architecture. And finally, I will be talking about porting your code from ARM NDK to x86 NDK or the NDK or the Android application for the Intel architecture. So what is Intel working for Android? Intel is one of the key Android open source providers, and it also contributes to the kernel development. Also, in association with Google, Intel develops the drivers, it develops the firmware, it optimizes the Android drivers for Intel hardware. The other things which Intel is involved is in porting and optimizing the browser as well as applications for Intel architecture, and also to promote the NDK applications to bridge the technology and to ensure that optimum usage of the hardware resources are utilized. So these are some of the devices which have the Intel processor. So recently the memo pad was launched in the month of August. Asus Zen phones, we have the Dell Venue tablets, and the Minnow board and Intel NUC are the other devices which has the Intel platforms. So let us talk about Android NDK. So what is NDK? NDK, or the Native Development Kit, is a set of build scripts or is a toolkit which is provided with Android SDK. It's an add-on to the Android SDK wherein you can incorporate your native code, that is the code which is written in C or C++, into Android applications. This happens via an interface called as the JNI or the Java Native Interface. So why is it used? Whenever your application So why it is used, or why are the NDK applications should be developed? So whenever your application is doing any intensive task, whether it is when it is doing a performance intensive task like a signal processing, or you have a complex algorithms, or when you take games, whenever you have a display oriented or lot of uh, frames in your application, when you're using a lot of frames, you have to use the NDK applications. It allows you to take advantage of direct hardware access, thereby ensuring that you can execute your code faster. Through the NDK applications, it also promotes software code reuse. That is, if you already have a um, algorithm which is developed in C or C++ and it's a time-tested algorithm, rather than redeveloping or developing again the same code, re-implementing the same code in Java, you can use this existing code, ensure that your Java applications have points where it can call these native libraries. Let us look at the application development lifecycle. So first, you will be writing the C or C++ code, then write a makefile to compile this code. And when you're compiling the C or C++ code, you have to use some flags. I will be talking about these flags later in this session. And you will be calling, once the C code is compiled, you can call this particular functions from the Java using the JNI. Also, you note that you can debug your native application or the native source code through the GDB or GDB. So here, you will first develop the Java native library. Once this Java native library is written, you're compiling this using Java C to create a Java native library class. So from this Java native library class, there are two ways how you can implement your native source. One is a usage of Java H function, and the other one is the usage of JNI onload. So if you use Java H function, you will have to first create a If you use the Java H function, first you will have to create a header file, and then from this header file, you will be linking and compiling your C code. Whereas in case of JNI onload, this whole step of creating the header file can be removed. So that is the reason we have a box here. I will be talking about this later in the session. So once you're linking your C code, or once you compile and link your C or C++ source code into a dynamic library, you will use this dynamic library in your Android application class. So let us look at the C or C++ support which is present. For the NDK application development, the entire standard set of C or C++ functions are not available. It has a specific library called the Bionic C library, which is lighter than the standard GNU library. Note that it is not POSIX compliant. It provides access to the Android system properties and Android hardware layer, and also it does not have the system level IP calls or the inter-process communication calls. Note that your existing C code will not directly run on this for the NDK application. You will have to recompile this source, the C++ source, with the Bionic C library to ensure it runs with your NDK ensure it runs with your Java application or Android application. So let us look at the C++ support. It lacks the standard C++ support, as I mentioned in the previous slide. There are many basic functions like the string functions also which is not supported directly. It supports exceptions, however, and also it gives you other functions which are available specifically to the NDK, like the system run, like the STL port, the GNU STL runtimes. These are the other runtimes which are available with the C++ in case of NDK. So how to install the Android NDK? Installation is the Android NDK is available as a separate package on the Android website. So developer.android.com, you can download the NDK from there. Just unzip the downloaded files and your NDK is ready. Then you can integrate this NDK with your Eclipse ADT, Eclipse Android Development Toolkit. Through the preferences, just you need to specify the path where you have downloaded your or where you have extracted your NDK files. Let's look at how to add native code to an existing Android project. In the manual way, what you need to do is you need to create a JNI folder under the application folder. Under this JNI folder, you need to place all the header files, the native source code, that's the C or C++ source code, and also ensure that you are keeping the android.make file here. So android.make file contains the build instructions of which files needs to be compiled and what is the library which needs to be created, etc. Then you build the application or the NDK, the C++ library using the command ndk build. So ndk build script automatically looks for the JNI folder and it takes the source code from using the build file, that is the android.make file. It takes the source code, the C++ files, and compiles and creates the shared object libraries. So if you can see here, once you run the ndk build script, the ndk script will automatically create the library folders under the libs folder. So here you can find the x86 folder in this image. Now let us look at an automatic way of adding the NDK support to your Eclipse project. So you need to right click on the Eclipse project, go to the Android tools and click on add native support. So once you do that, android.make file and a C++ file will be automatically created. Next comes configuring the NDK targets. So there are many processor chains or the many processor architectures which supports the NDK as of now. One is the ARM. The ARM supports two versions. One is the general ARM and then ARM v7. Then you have x86 libraries and also you have MIPS platform, that is the PowerPC platforms. This can be specified, like which are the platforms you are targeting can be specified in a file called application.mk, that is the application make file. So there you can set the flag called app_abi to the architectures to which you need to develop your application or to which you are targeting your NDK application. Next, we will see how to integrate your native functions with Java. Note that the Java types and the C++ types are different. So if in case you are performing any operations, if you are performing any operations on the Java objects or the any operations on the parameters, you need to ensure that you are declaring the following native types in your C++ file. This is because the sizes of the primitive types are different in Java as well as the native. So int, the Java int, you have to use it as jint to ensure that you are getting a 32-bit signed, you are creating a 32-bit signed variable. First, when you are declaring or when you are defining your Java native class, you need to use the keyword native to tell the function or to tell the compiler that this particular function has to be looked up in your native class, or this is the function which is existing in your native class, and you need to run the you need to execute it from that particular folder or that particular library. Also, you need to load your shared object file. So whenever you are writing your native library class, you need to know what will be your native class name. So this has to be called at the end of the function. There are two ways how you can associate your native code with a Java code. One is a Java H method, the other one is called the JNI onload method. I have spoken about these two variants when I was explaining you the whole flow of NDK platform. So let's look at the Java H method. Java H is an application which is part of JDK, which helps automatically generate the JNI header stubs based on your Java native class libraries. So to run Java H method or to run the Java H command, you need to have the Java compiled classes ready. This is the command which you will be executing to create your JNI header stubs. In the Java H method, you can see here under the JNI folder, you have a hello.jni.c. This hello.jni.c is created from the header stub which is generated automatically. If you look here, this is a stub or this is the function name which the Java H has automatically created for you. You can see that it has a long name for the method, that is java underscore com underscore example underscore hello jni underscore hello jni and string from jni. Whereas string from jni is the only class name what you are calling from your native class file or the Java native class file. When it comes to the C file, automatically JNI creates this long name where it mentions this function is called from Java. com.example.hellojni is your package name. So that is the com underscore example underscore hellojni. Then you again have this hellojni, which is the class name from which you are calling this function. And finally, the name of the function, that is the string from JNI. Then the other method we have is the JNI onload. So a question comes up like once we have the method of Java Edge, what is the point in having another method like JNI onload? The reason of JNI onload is it's a proven method. Proven in the sense the whole entire Android open source project, the NDK platform, NDK architecture is built based on this architecture. It is built based on the JNI onload method. There are no more surprises after methods registration. That is, once you register a native method with a method in the Java source file, you will not have any surprises at the runtime. In case of Java Edge, there are chances that your application will crash during the runtime. Whereas in case of JNI onload, any error you will get to know during the compile time itself, so that you need not wait until you deploy your application to an emulator or to a device. Third thing, it is less error prone because then you can define your custom names to the native methods. There is no need of creating this long names as I showed you in the previous slide. Then it allows you to add or remove the native functions, so thereby you need not recompile the whole header stub recompile, or you need not run every time Java H method to create a new header stub whenever you want new functions from the Java source. And also it won't have a symbol table issue when you're mixing the C++ code. So what we do in the JNI onload method is this string from JNI. This is a function which is present in your C++ code. So if you remember in the previous slide, it was a length, like the name was too long, that is Java underscore, etc., etc. But here you can find that it is a single or a smaller name string from JNI. Then what you need to do is you will be creating a JNI native method type of array, wherein you are loading all the native methods which you are exposing, and using the JNI onload function, you are registering the array. So you are registering in the array, you are mentioning to the JNI runtime that these are the methods which are exposed to my Java class. So these are the methods which can be used in the Java class. And this JNI onload function has to be implemented in your C++ file. So now let us look at a demo. So here I have a Fibonacci series application, and this is my native Java class. So I have implemented two functions in Java, fibj and fibji. So fibj is the recursive function wherein you're calling the same function, you recursively calling the same function to find out the Fibonacci value, and fibji is the iterative version wherein you are using a for loop to perform the same action. In this file, you can see that I have two files, fibn and fibni. So these two files, if you can see, I have used the keyword native. So the moment it sees the keyword native, it knows that this function is implemented in a native function. This is a native function implemented elsewhere. And how does this particular function know where to look for the these functions? So here at the end of the file, we are loading the library. So I'm calling my library as nfib. So I am loading my library here. So let me first go through the Java H method. So if you can see, I already have a JNI folder and I already have this jfib.h which is created. So let me run the Java H once again and see if it updates the header file. So from the command prompt, I'm running this java h-d denotes the path where the output files need to be generated. So this has to be JNI because the NDK build script automatically looks for the JNI folder to compile to find the source code and find the source files and build a shared object library. So this always has to be JNI folder. Then I'm providing the class path here. So that is bin classes com.hol.fib series. This is my package name, and then jfib is my class name. So it's executed. So you can see that it has created this header file for me. So from this header file, I have created a native fib.c file. So you can see that JNI export JNI calls are here. So this is my function name java com hol fib series fibn and fibni. So since this has to be the first function has to run in a recursive format, I have implemented a local function that is jint fibn and jint fibni. So these two functions executes and I send back the results from the original functions which have been created. So let me do a NDK build here. Before running the NDK build, let me show you the android.make file. So in android.makefile, these are some of the standard flags which needs to be set. It is the local path, that is to the call to my current directory. The local module, what is the name of the library which needs to be created. Then which are the source files the ndk build command has to build to create the shared object library. So here right now I'm using only one file, that is the native fibc file. So let me run the ndk build. So you can see that it has created files for ARM v7 architecture, the general ARM architecture, x86 architecture, and the MIPS architecture. So I have specified in the application.make file that it needs to create libraries for all the platforms. So here I can be very specific. Let me do just an x86 now. So if you see now, it creates library only for x86 platform. So once this shared object library is created, I already have a pre-built interface from where I have been calling these functions. So here you can see that first I am calling the Java functions jfib.fibj, jfib.fibji. If you see that this is these two functions. And then I'm calling the native functions fibn as well as fibni. So let me start an emulator and run this application. So while the emulator starts, let me talk about the JNI onload method as well. So copying the entire source code from the native fib.c, I have created the C++ file. So JNI onload generally works with the C++ file. So if you are having a C function, preferably try to use the Java H method. So here the same functions have been moved inside a namespace. And once I've done my implementation, you can find that I am registering, or I am creating a method table, an array of type JNI native method, wherein I am mentioning the name in the Java source file. So fibn and fibni is the name in the Java source file. Fibn and fibni. And fib cppn and fib cppni are my functions which are present in my C++ file. So the difference you can directly note here. I am using a custom name whatever I want rather than having a standard structured name provided by the Java H method. So once I create this array table, the method table, I implement the JNI onload function, wherein first I will get an access to the current environment, the current Java environment. Then I'm getting the reference of the jfib class, and from this jfib class I am first registering the native methods. So I'm registering this method table, and I'll delete the reference to this particular class. So that's it. This is all it takes for the JNI onload. Okay, so now that my emulator is ready, let me run the existing code. So 10 is a lower number where you have almost same time used between Java code and the C++ code. Let me try giving a higher number. So just as don't take it in the literal terms, but you can see that the native functions are comparatively running faster when compared to the Java code. So this is just a demo application, and this does not conclude anything whether the recursive functions or the iterative functions are faster in native or faster in Java. So let me go ahead and now show you the execution of C++ file. So what I'll need to do is I need to go to my android.make file, and instead of native fib.c, I need to specify fib.cpp, do an ndk build again. So now that is ready, once again, let me go ahead and compile and run this application. So you can see the similar kind of output. So that is with the demo. Now coming back to the presentation. So I will be talking about how to handle the JVM objects and the Java objects from the native code. that is from the C, C++ code. So memory handling of Java objects is done by JVM. So that is done by the Dalvik virtual machine. So we need not worry about that. Whereas when the reference for these objects are taken, or you are sending the reference of these objects to the native libraries, in the native library you need to delete the reference when you're exiting from the code. So at a time you can use only 16 references to the Java object in the native libraries. So though it says that local references are automatically freed, it is always a good habit that you delete manually the reference to the Java object whenever you are exiting from the native libraries. So now let us look how to create a Java string in the C, C++ file. So you have to use the following syntax to create. So you have to use the following syntax to create string in C file, Java string in the C, and this particular format to this particular syntax to create in C++. So you can see that the main difference between the C and C++ is the nature of env variable. Otherwise, the functionality or the method to be called is the same. Next, what we'll do is we'll see how to get a C, C++ string from the Java string. So that is in the native file, how to get a Java string copied to a C or C++ string. So this is a syntax which is used generally, wherein from the environment variable you are calling the get string function, and you're giving the name of the Java string and also null as a parameter. You're passing the null as a parameter. However, more secure and efficient way is usage of this particular syntax. So once we are seeing how to get the string or how to create the string, we will see how to handle the Java exceptions. So handling Java exceptions in the C or C++ is like this. The other one is the throwing of Java exceptions from the native code. So all the time you will not be able to handle the exception. If in case you have to throw a Java exception, this is how you will be doing it. First, you will be getting the reference to the Java exception class, and once you get the reference, you are throwing the message through this particular class. As you can see, the exception will be thrown only when you return the call back to Java. So in between the native function, you will not be able to throw the Java exception. So that needs to be handled. So the moment there is an exception, you need to throw the Java exception and immediately return back to the Java function. Now let us look at optimizing your source code for the Intel architecture. There is a method called vectorization through which you will be optimizing your source code for the Intel architecture. On Intel, it is called the SIMD instructions. So SIMD instructions are available up to the SSS E3 version on the Intel architecture platform. So SIMD is single input multiple data. So with the SSS E3, you can perform operations up to 128-bit at once. In case of ARM architecture, you will be using Neon instructions to do the same. So the vectorization for Intel architecture can be done in two methods. One is the compiler does the vectorization automatically, or you can manually specify which particular instruction needs to be vectorized. Let us look at the compiler optimization. So by using these flags in GCC, you can automatically optimize, or you could automatically vectorize your instructions. So fast math is the rounding of the floating point arithmetics. And the other optimizations, that is the mtune atom msse3, this specifies the level of vectorization it needs to perform. Now we look at the last part of our discussion or the session today. It is porting your existing ARM NDK code to the Intel architecture code. So the Dalvik applications are platform independent. That is, these applications can run on any Android device. It does not matter if it is an Intel device or an ARM device or a MIPS device. Whereas NDK applications which are built for ARM devices generally can run on Intel devices because of the existence of a libhoudini. So libhoudini is a library which is present in the Android devices running on Intel architecture. It's a library which converts the ARM instruction, or which converts the runtime, or which translates the binary source from the ARM to Intel during the runtime, and it executes the command. Note that though the application runs, you can find there is a lag in the application. You can find the application is not running in an optimized way, how it runs on a native ARM device. So to get a better performance and to ensure that the power consumption is reduced, what you have to do is you have to recompile your library using the x86 flag, or for the x86 platform. So as mentioned in this slide, it may be very easy as just adding a x86 in the app_abi flag and rerunning the NDK build. Or if there are any specific instructions, or if you see like there is a scope for improvement or a scope for optimization for Intel platform, you need to make some changes to your application, to your applications, and then compile the code. One of the basic differences between the ARM architecture and the Intel architecture is the memory alignment. By default, ARM always takes a double memory alignment. So if you can see for this particular structure where you have two int variables and one long variable, you can see that ARM allocates equal memory to all the variables. So even for int, it allocates 32 bits, even for long it allocates 32 bits, and etc. Like, so totally you can see it is allocating 3 blocks of 32 bits for this particular structure. Whereas in the same structure, when runs on an Intel architecture, it allocates differently. So you can see that for int, it is allocating only 16 bits each, whereas for ARM, for as long, it is allocating 32 bits. So thereby there is a difference in the memory alignment between the Intel architecture or the x86 architecture and the ARM architecture. The easiest fix for this would be to ensure that you have this double aligned for both x86 architecture. You have this double aligned flag set, so that for both ARM as well as x86 architecture, it allocates the same number of blocks. So as I specified during the vectorization, neon instructions are for the vectorization techniques for ARM platform, whereas for Intel platform, it is the SIMD instructions is the SSS E3. one of the easiest way where uh, you can wrap your neon function is by using the neon versus sse.h file. So this has a neon function wrappers for all the neon function, and also it has intrinsics, and it is very specific to SSSE3. Thereby you'll get the Intel optimizations for all the neon instructions. So with this, we come to an end of the session today. These are some of the resources which are available. So you can refer to the developer.android.com for NDK. You can refer to the Oracle website for the JNI documentation. So this provides a detail as to how to write the functions using the Java H method, how to write functions using the JNI onload method. And for more details on the Android for Intel architecture, you can visit the website software.intel.com/Android. For any feedback, questions or comments about this session, or if you want any specific session to be covered in this webinar series, you can send us an email to the intelapps@beahead.biz. You can contact me through my Twitter handle, or you can contact me through my Facebook ID. Thank you.